Today, we will still do some things from day 2, from yesterday, because we yesterday didn't finish. It was like, we are a little bit slower because we write everything. We don't use slides and so on. So, and I was also hoping that maybe of you will prove it as an exercise yesterday, the Shannon bound. So we would like to prove the Shannon bound. Shannon bound. Do you remember what was that? What was that? 3/2 of delta, yes. So we have a multigraph G to the theorem, and Shannon G, loopless multigraph. Then chromatic index of this multigraph is at most 3/2 delta G over 2. Okay? So we want to prove that. For simplicity, let's just delta instead of delta G, okay? For simplicity. Now, we're gonna prove this by induction on the number of edges. And induction on number of edges. So we denote by m the number of edges, yes? M is the number of edges. Now, if the base of induction, let's say it like base of induction, if number of edges is at most 3 delta over 2, then we are done, yes? We color all edges differently. Yeah? Color all edges differently. And we are done. Okay. So now assume that n is bigger than 3 delta half, and assume theorem holds for m minus 1, and we prove for m. Okay? So by induction, we can, so our graph G has m edges, and the claim calls for m minus 1. So we can color all edges of G except E1, which is UV. Okay, I draw it now here, U. So here is U, here is V. We can assume only this edge is not colored. Everything else is colored. Okay. So I use the same notation as before. Do you remember what means? Let's write it to be more precise. Let's write it. Now the number of colors is, the set of colors is 3, 2 delta, yes. the colors of this, yes. Do you remember from yesterday what's mean all of you? Colors not use it in you. Okay. And all of you. Colors not use it in you and we. Can you tell me what is the size of these sets? How much is all you? We have 3 delta colors and use it at most how much? Delta minus 1. Delta minus 1, I use it here. Yes? Because this is not colored. So minus delta plus 1. Yes? This is like delta half plus 1. Do we agree? Is at least. Similarly, O of V is at least, let's write it like this. For both of them holds this. Okay? So we can say this is claim 0. I have not named it claim 0. Claim 0. Claim 0 says that these sets our size at least delta plus 1. Delta half plus 1, yes. Okay, this is claim 0. What do you think? Are these lists disjoint or they can have some common element? Yes. Claim 1 if that these sets have empty intersection. Otherwise, if alpha belongs in the intersection, yes, if alpha belongs in the intersection, then we can put here alpha. There is no problem at vertex U because alpha doesn't belong to O or Q. Also no problem at vertex V, and we are done. Okay? So this is claim 1. Claim 1. This is claim 1. Okay. Claim 2. Claim 2. If alpha star belongs to O of V and beta star belongs to O of U, then we have alpha star, beta star, color it path between U and V. This is claim 2. We're going to prove it now. So let's take this drawing. Let's take this drawing a little lower. Copy. Okay. So alpha star doesn't belong to all of V, yes? Alpha star doesn't belong to all of V. There must be appears at U, yes? We're gonna have here edge colored with alpha star. Beta star doesn't belong to all U. So it must, by claim 1, this is by claim 1. So beta star will appear here. Now I take this Kempe chain path. So here, if here is alpha star, I come to here. I go further. Graph is finite. I may end in some vertex which is different than U. If I end in some vertex which is different than U, however I finish here, this is vertex 6, and let's say X is different than U. Then what do you propose we do? Change the colors. So we change the colors. This will be alpha star. This will be beta star. This will be alpha star. This will be beta star, and so on. And what we can put now here? Beta star. Yes, we put beta star here, and we color it. So, and then we are done. So what left is we must assume, it must hold that this path, this green path actually finish at U. And then we cannot do this. If this path, I will now clean it a little bit. If this path, so then we are doing a little bit something what left from yesterday, as we didn't get enough time because we write everything and we're a little bit slower. So then we have, our path is like this. And it doesn't help. If I change it, here will disappear beta and will show up alpha star. Here will disappear alpha star, will appear beta star, and nothing helps. So, but this is the claim, that there must be such path, yes. Okay? Now we fix, now we go further, fix alpha, which belongs to, which missing at V, and beta, which missing at U. Okay? This is claim 2. Okay? I take my drawing again. Copy it. And a little bit clean it. So alpha is missing at V. And by claim 1, what we know? It appears at U. Let's say this is alpha. Let's say this is HE2. And it is W. This vertex is W. It has color alpha. And we know that we have here some vertex must show up beta. Our next claim is, what is claim 3? what I did done. What do you think? What will be the claim 3? Can you guess the claim 3? What will be intersection? Empty set. Why it's empty set? Because if I have here color, let's say P, okay, that is missing. So what that means? P is missing at U and P is missing W. So what I can do? I can put here P as, and I can move alpha here. It's no problem at V because alpha is missing at V. Okay? There's the proof of claim 3. What is the size of this set of UW? The size, observe that the size of W here is at least, it is colored vertex, yeah, colored edge. Maybe everything is colored. Maybe everything is colored. So we're gonna have 3 delta minus delta at least delta half. Okay? This is observation. Claim 4. Claim 4. Claim 4 says this set here and this set here of missing colors must have something in the intersection. So OW intersection OV is not empty set. Okay? Suppose it is false. Suppose here is equal. They have intersection. So, but look the claims 3 and claim 1. Claim 3 and claim 1. You can still see us. Claim 3, claim 1 says what? O of V intersection O of V is empty set. This is claim 1. Claim 3, what says? O of U intersection O of V is empty set. And we now assume it with blue. O of V intersection of V is empty set. So all these 3 sets are pairwise disjoint. Yes? So let's count how many the number of colors have together. So if these are a disjoint set, then we're going to have OU union OV union OW will be, because these sets are disjoint, will be number okay? Because these three sets are disjoint. From this follow this equality, yes? Let's count on how many we have. O, U, and V, they are delta half plus 1, yes? They are delta half plus 1 plus delta half plus 1 plus delta half is W. Look, this is more than 3 delta half, strictly more, which is the size of all colors. So delta half plus 1, delta half plus 1, delta half. So this is more than, which is 3 delta over 2. So this is not possible. So this assumption here is wrong. This proves claim 4. Okay? So we have, by claim 4, exists some gamma which is intersection of OW and OV. So gamma missing a W and missing a V, yes? Let's take the figure again. Our figure. So we have, a way to correct the figure. So gamma is belongs here, yes? Is missing at V and is missing a W. Now let's have a look in claim 2. For any alpha star that missing in OV and any beta star which missing in OU, there must be path like this, connecting from U to V that alternating. So I will say, I will take here the same, in this claim I will take beta star to be beta and alpha star to be gamma. Because this claim is for any alpha star and any beta star which is satisfied. So we know that beta, that was assumption, beta is missing at U, and gamma is missing at V. So there will be alternating path with beta and gamma from U to V. Let's draw it. Let's use some other color. So we're gonna have like, here will be first, because this gamma is missing, here will be like gamma this will be gamma, then we have some beta, then gamma, then beta, then gamma, and so on. We have such path P. My question is, can it happen this W belongs to this path? Can it happen that, can it happen gamma belong, no, this W, W belongs to this path. No, Yes. No. What is the reason why not? Look, at every vertex here, intermediate vertex, every vertex is incident to a edge gamma and edge beta. So if a vertex belongs here, it must be incident with edge colored gamma. And look here, gamma belongs to OW. So W doesn't belong here. Okay? So what we can do? We can now recolor here with beta, with gamma, with beta, beta, gamma. This is okay at vertex V because at vertex V, gamma was missing. This is okay at vertex U. Yes? Why it is okay? Because beta was missing at U. Yes? Now it's here. Okay? Okay. So now here we will lose color alpha here. Okay? And what should we put on UW? Yes, we put here gamma. And we color the graph. That's it. So this is this famous Shannon bound 3 delta over 2. The proof is not very complicated, but it's not simple too. Yesterday I leave it for exercise, but I didn't have time to do it. Then I leave it for exercise. Nobody wanted to solve it, so we did it now. Okay?
You take all the OFU and OFU of W.
So,
when we take the cardinality of OFU, OFV, and OFW, we get it to be at least the total number of colors.
yeah, this is obligation. So this assumption is wrong. This assumption is wrong. This cannot happen.
W are not isolated.
These two are disjoint. And if these two are disjoint, we get more than 3 delta half colors. So these two cannot be disjoint. These two must have color together. And this color then I take should be gamma. Okay? Is it clear? Okay, our plan was official that we do a little bit normal edge coloring, so I must speak about that. We like it or we don't like it. It's life. A little bit new topic. Should I use the slides to go faster or no? Or like this? Sorry? Give you slides. So you prefer slides? They don't get that we are into trouble with time. They don't understand. So okay, let's do define it. Let's go like this. Yeah, normal edge coloring. Actually, what is important, normal edge 5 coloring. We're going to use 5 colors. Okay? Originally, it was defined first Petersen edge coloring, Petersen graph edge coloring, and then the normal coloring was introduced. We go other way around now. Maybe this way is more simple. We will use the colors from 1 to 5. Our graph is cubic. Okay? Now, UV. I will use notation if here is color A, graph is colored A, B, C, and this is vertex V, then I will say sigma of V are these three colors. Okay? So if sigma of U union sigma of V is 3. So we have the same three colors at U and the same three colors at V. For example, it can be like this. 1, 2, 3, 2. What should be here? 1, yes. Then we say it's poor edge. Such edge is poor. I mean, for the edge UV. UV is poor edge. Poor because it has the smallest possible number of colors. Okay? If this union is equal to 5, then UV is rich. Like so if UV is rich, what should we have? What should we have here? 4 and 5. Let's say 4 and 5. Then it is rich. So we like to have all ages, poor or rich. So we say edge is normal. If it is poor or rich. So we interested in coloring, 5 coloring, which is normal. Okay? We are interested which is normal. So normal coloring is 5 coloring with all edges being normal. Okay? This is a very huge conjecture. Every bridgeless cubic graph has normal coloring. This is one of the hardest conjecture in graph theory. The strongest one. Maybe it's the hardest. François Jaeger, GG, from France. This is one of the hardest conjecture in graph theory. Maybe it's not true. Implies many other conjectures. Okay? Now, can we prove it for Petersen? Check it for Petersen. I give you 1 minute. Okay, I will do it for you. Do you know what is Kneser graphs? So do you know that Petersen graph is a Kneser graph? Let's denote the vertices of Petersen as it requires the Kneser graph. Uh, so I will explain. Just let me do it first. Yes, 3, 4. Then we have 1, 2, 5, 2, 5, 1, 5. So we have like 2, 4, 2, 4, 2, 5, 4, 5, 1, 3. Here will be 2, 4, 3, 5, 1, 4, 1, 4, 2, 3. Okay. We take all two of size 2 subsets from 1 to 5. All subsets of size. There are 10. And then we put 2 subsets connect if the intersection is empty. You see 3, 4, intersection 1, 3, 0. 1, 2, 3. And if we do this, this is the vertices, yes, the vertices there. And if we do this, we get the Petersen graph. Okay? And now we have this drawing then, yes? Now let's put on every edge the color that is free. Look, is here color? I would like to put here the color. I would like to put here the color that is not here and is not here. Is not here and is not here. Which one? Let's do that. We put here 5. Yes? We put here 4. We put here 3. We put here 1. We put here 2. We put here 3, 4, 5, 1, 2. We put here 4, here 1, 2, 3, 4, we put here 5, 3, put here 2. You can check that this is normal coloring. Such that every edge is rich. Every edge has all 5 colors. This is a normal coloring. You can say even this is a rich coloring. Okay. This is the basic, the smallest thing what we must know about normal colorings. But there is another little bit more confusing coloring which François Gégé introduced before this normal coloring. It's called like Petersen edge coloring. Petersen edge coloring. It says, I will, for shortly, P10 will mean Petersen graph. P10 will mean Petersen graph, okay? P10 coloring. One more notation. When we have graph H, let's say, and let this is vertex U and this is its incident 3 edges. We always speak about cubic graphs. I don't know if you use this notation. Delta of U is denoted by E1, E2, E3. It's little delta, okay? Okay, now we define Petersen coloring of graph definition, yes? P10 or Petersen coloring of some graph G is mapping which maps edges of graph G to the edges of graph P10 that maps edges of graph G to maps of the edges of the Petersen graph. So actually we color graph G with the edges of Petersen graph. It's a little bit complicated, yes. Such that for every vertex of G, for every vertex of G exist W of P10, vertex of P. This is vertex. Now this is on the way a little bit, such that holds this phi of edges of in graph G of V are equal to the edges of no, here is not edge, here is P10. I know that you don't understand now what I'm talking, yes? We color of graph G the edges of the graph G with edges of Petersen graph. But if in G we are here, we have some vertex V, and we have, let's say we put colors A, B, and C. A, B, and C are edges of Petersen. What is this requirement says that in Petersen, these three colors must be incident. These three, which are edges in Petersen, must be incident at the vertex. Okay, this is a little bit more complicated. But actually, look, this is Petersen graph. I can denote my edges, vertices with 1, 2. When I say 1, 2 vertex in Petersen, I mean to this vertex. When I say 3, 4, the vertex 3, 4 in Petersen, I mean on this. When I say 1, 4, I mean on this. Yes? So, at 1, 2, vertex 1, 2, we have 3. With 3 edges, yes? 5, 4, 3. We can use them as a colors too. We can use them as a colors. So, we can always in Petersen say, oh, this is 1, 2, yes? Let's say 1, 2 vertex. And then I will have to have here colors 3, 4, 5. Actionable time. So, original conjecture of normal edge coloring was stated in this incident Petersen edge coloring and says conjecture, original conjecture. Yeah.
The function from P to G to P to P of 10. You said that there is a function for the Petersen edge coloring. You said that there will exist a function from P to G to P to P of 10. But you meant that we will color the original graph G with there are 15 edges in P of 10.
Yeah, we have 15 edges.
We will use 15 different
Yeah, we use 15 different colors. So, let's do an example. We have some big graph G. This is the graph G. So, let's say I put here vertex. So I map vertices of G into vertices of H. Do we agree with this? Of Petersen graph for me. So let's say this is mapped in 1, 2. Okay. This one, if I map, let's say 3, 4. Okay? 1, 2, 3, 4. 1, 2, 3, 4. Okay? Then the edge between them in G will be actually this edge. Be careful, there are more edges with 5. But they're different. This is like 3, 4, 1, 2. This is 1, 4, 2, 3. And this is 3, 4, 1, 3. So there are actually 3 edges. When I say edge 5, there are actually 3 edges. Depend of what kind of 2 sets I have on the end vertices, yes? So this is this 5 with 1, 2, 3, 4, yes? And then maybe I go from 3, 4. Okay, I go to 5, 1. Then this edge, which will correspond, will that edge 4, which have for n vertices 3, 4, and 5, 1 in Petersen graph. So this is how I map.
Isn't this possible map the vertex set of G to vertex set of theta?
Yeah, we must map it. We must map it. Sorry?
It is only possible for cubic graphs.
Two?
Cubic graphs.
Yeah, we speak all the time speaking about cubic graphs. Yeah. This is correlated with snarks. This is related with snarks. Yes. And then originally this conjecture was stated like this. Petersen edge coloring conjecture. Every bridgeless cubic graph G is Petersen edge colorable. Okay? Every cubic bridges graph is Petersen edge colorable. Can you color the hypercube? I color the hypercube very easy. So we map also all vertices of this graph into the vertices of Petersen. I will map all these vertices into the vertex 4, 5. So I will not complicate it mapping in different vertices of Petersen. And then I will have here H1, let's say 1, 1, 1, 1. I will have here 2, 2, 2, 2. Then I have 3, 3, 3, 3. At vertex 4, 5, I have 3 edges, yes? In Petersen graph. Look. I take this edge. I will take this. I will take this figure a little down, yes? Look. At edge 4, 5, where is 4, 5? This is 4, 5. I have 3 edges, color 3, color 2, color 1. So I will map all my vertices of hypercube into the vertex of Petersen 4, 5, and I will color 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This is possible for every 3H colorable graph, not only for hypercube. Do you agree? I do the same. If graph is color it 1, 2, 3. I will take this to be vertex 4, 5 of the Petersen, and I have Petersen edge coloring. Okay? So this is true for all 3 edge colorable graph. So in order to solve conjecture, this conjecture, you have to solve for snarks. This is why snarks are very important. And this Petersen edge color conjecture is actually a reformulation of this. Actually, Petersen edge coloring conjecture first appeared by Gégé, and then Gégé discovered normal coloring and restated with this. These two conjectures are the same. It's the same conjecture, just they use different notation. With small observation, it can be easily seen that they are the same. And this is actually one conjecture, just stated in normal coloring notation, or just stated in these mappings of graph into Petersen edges. Yes, this is the other notation. This is the original notation. Normal coloring is like a little bit easier to deal with because we are used to do colors, with colors to color the graph. We are not using so much coloring of one graph with the edges of another graph. It's a little bit difficult for us to digest this notation. So this is why it's very nice that Gégé came out with this normal coloring. And this conjecture, what is the time? And this conjecture is very big conjecture. Like this Peter edge let me finish this part and then we're gonna have break, okay? Petersen, I can make it like this. Petersen. Conjecture easily implies Fulkerson conjecture. Do you know what Fulkerson conjecture says? I have cubic graph. If I double every edge, then I will have graph of 6 regular graph, yes? So if I have cubic graph, now I double every edge, and so on, then this graph is 6 edge colorable. This is Fulkerson conjecture, it's very famous conjecture. This is very trivially implied by Petersen edge coloring conjecture. Because if Petersen coloring conjecture is true, okay, you can check that this Fulkerson conjecture is true for Petersen graph, then you will map any graph into the Petersen, and correspondingly, depend with which edge is colored of the Petersen graph edge, this edge of the regional graph, you double it, depend how it's colored the Petersen, yes. We don't have too much time to go into details here. It also implies cycle double conjecture. Actually implies the cycle double conjecture into stronger form, which is known like 5-cycle double conjecture. Cycle double conjecture is in a graph to find a set of cycles. Here, cycle may mean doesn't have to be the cycle connected. You can have disjoint cycles and so on. More wider notation. And it says that every Bridges graph can be covered with 5 cycles. Cycle actually is the union of circuit. Circuit is what we know C2, C4, C5. This is a circuit. And this is very obvious that it's true in Petersen. This is obvious that this we can do. And then if Petersen edge coloring conjecture is true, for any graph, I can map my cycle double cover of Petersen into a cycle double cover of this graph. And then you take four line, this funnel plane 4-line conjecture, funnel plane 5-line conjecture, and many other conjectures. They are all true for Petersen. If Petersen edge coloring conjecture is true, it implies immediately. So Petersen edge coloring conjecture is on the top and implies many important conjectures. Imagine you solve it. You will be very, very, very famous. So try tonight. We saw it after lunch. Yeah. So, okay, I will stop here. I wish it also this part explained better, but we ran it out of time. We have today to do work planar graphs and we don't have time for edge coloring. So we take 1 hour and it is more than enough. We cannot afford more. So if you wish, study this yourself and you will see it's very beautiful theory.